darlings, welcome to this video on polar versus nonpolar. This is in Unit 2, Section 3. You'll go ahead and you'll need your notes, pen and paper, and Table S. So let's talk about electronegativity. This is a measure of an atom's ability to attract electrons, or a measure of the ability of an atom to attract electrons. So pretty much how much an atom wants an electron. So you'll use Table S to help you out with this. Table S gives you a whole value of electronegativity, and that's in this column right here. Remember back from when we talked about the periodic table, fluorine, let's find, fluorine's right in here. It has a value of 4.0. That has the highest electronegativity value. Francine, which is in the bottom left of the periodic table, has the smallest electronegativity value. The most common ones that we'll use during today's video is hydrogen, which is 2.2. We'll also use carbon, which is 2.6. And nitrogen, which is 3.4, hidden under that fluorine. So we'll talk about polar versus nonpolar. Polar is just having an unequal distribution of charge. We've seen this when we talked about how water bends in the presence of a charged wand. It has dipoles. One end is positive, the other end is negative. And we've seen this using that arrow. So that arrow, where we point to the negative, this will be partially negative. And we show a plus sign here for partially positive. Nonpolar molecules or bonds will have equal distribution of charge, and they do not have dipoles. We won't show those arrows for this. So, the easiest, or probably easiest thing to miss or get confused are polar versus nonpolar bonds or polar versus nonpolar molecules. So here we're going to talk about polar versus nonpolar bonds. So make sure you highlight the bond section here. This is checking for electronegativity difference. So let's through. Electronegativity difference is just using Table S. So we will check to see what the difference is, and we can use delta EN to help us abbreviate that. We use a line in order to kind of chart where everything would be. So I'm going to have a line here, or excuse me, a line all the way left, that's 0. The one all the way on the right is 4. This is 1.7, and this is about 0.5. It's not that great, but it's there. From 1.7 to 4 is ionic in character, meaning that it's positive and negative versus partially positive and negative. 0 to 1.7 is going to be covalent. When we have 0 to 0.5, those are nonpolar. And 0.5 to 1.7 tends to be more polar. Now this is in a continuum, meaning the closer it is to 1.7, the more ionic it is compared to something at 0. The closer it is to 0, the more nonpolar it is compared to something that's closer to 4. Alright, so it's one big continuum. Here is a nicer, neater way of showing this, so make sure that you get this down in your notes. It's an extremely important thing to remember. So, again, we're dealing with bonds here. We have to check the electronegativity difference on Table S. If it's polar, the electronegativity difference will be from 0.5 to 1.7 in that general range. The more polar it is, the closer it is to 1.7. Let's get that in there. Yep, sorry. The more polar it is, the closer it is to 1.7. The more nonpolar it is, the closer it would be to 0.5. So our example was HO. So from Table S, we'll find the values of hydrogen and oxygen. Hydrogen was 2.2, and oxygen was 3.4. And eventually you'll start to memorize some of these, especially these common ones. One thing to note is that this is absolute value because we don't have anything that's negative, so we obviously want to find something in the positive range. So we subtract 3.4 minus 2.2, that's a little bit easier to do. That ends up being 1.2. So 1.2 falls around, let's see if that's 1, maybe around here. Okay, it's still polar, it's a polar bond. Versus a nonpolar bond would be from 0 to 0.5. CH is a common example, so you'll see that a lot. Make sure that you highlight that CH. That tends to be a nonpolar bond. If you see that, that's a quick time saver for you. Because, let's calculate this. we have carbon and hydrogen. Carbon is 2.6 minus hydrogen, which is 2.2. That gives you 0.4. So that falls right here, which is in the nonpolar range. Any of those Hunkelbriefs will also be nonpolar bonds because those Hunkelbriefs are attached to themselves when they're not attached to anything else. So you have H2, for example. If you look at H2, which is H and H, 2.2 minus 2.2 gives you 0. It's nonpolar. So that's a quick time saver for you, especially when it comes to multiple choice. So again, you're using table S when you're looking at the bonds. Here we're going to look at the molecules. So this is polar versus nonpolar molecules. We've seen this when we talked about intermolecular forces, the attraction between molecules when we did that lab. We look at the symmetry of the molecules and we look for any lone pairs. Polar molecules have an unequal distribution of charge. They're asymmetric. Whereas nonpolar molecules have an equal distribution of charge or even distribution of charge. And they're symmetric. An example of this would be any of those Hunkelbriefs. So we have the 4 molecules that we tested in the attractions between molecules lab. This is when we had the charged wand. And we tested to see what would happen in the, to the stream of this liquid in the presence of a charged wand. So we will look at the molecules themselves. The one we have over here is water. We have H2O. There's lone pairs of electrons over here. So there's more more electrons or more negative charge towards that oxygen. The hydrogen has more positive charge. So we draw the arrowhead, point to the negative, and then the plus sign is towards the positive end, or part of the positive end. So overall, this is an unequal distribution of charge. We can also look at the symmetry of this. Sure, if you cut this in half this way, you have symmetry. It looks even, right? However, if you cut it in half this way, there is no symmetry. And that line's a little bit further, so cut it in half there. There is no symmetry when you fold it along that line. It's an asymmetric molecule. It should be polar. So let's take a look at this one. Now, let's remember what this molecule is. It has 2 carbons. So 1, 2. That prefix for 2, organic prefix for 2 is eth. I will squeeze it in right here. There's single bonds between those carbons, so it's eth-an for an alkane. And it has C double bonded O, OH. That's an organic acid, so it's ethanoic acid. Alright, just to remind you guys how to name these things, because that's still really important. Alright, now let's take a look at the distribution of charge. So here we have lone pairs of electrons there and there on the oxygen. So there's more negativity, or more negative charge towards that oxygen. That carbon tends to be a little bit more positive. Same thing here. So the oxygen tends to be partially negative, whereas that carbon tends to be partially positive. This has unequal distribution of charge and is asymmetric, because if you try to cut this in half, or at least show some line of symmetry, no matter which way you try to cut it, if you fold it upon itself, it's going to be asymmetric. So this is a polar molecule. Let's take a look on the bottom right. Name this molecule. We have 1, 2, 3 carbons. So I have prop. They're all single bonds between them, so I'm going to have AN in there. And it has an OH, so that's going to be all. I can name this 2-propanol, or the way we named it before was isopropanol. This is isopropyl alcohol, what you would probably find in your medicine cabinet right now. And let's take a look at the charges. Here, the oxygen has lone pairs, so there's going to be more negativity towards that oxygen, making carbon more positive. So there's an unequal distribution of charge. Also, when you cut this in half, let's see what happens. Sure, if you cut it in half this way, there's going to be some symmetry, but not really, because that hydrogen's right there, right? So there's not really symmetry there. If you cut it in half this way, there is no symmetry, because this OH does not line up with that H, right? So it's unequal distribution of charge, and it's asymmetric, so it's a polar molecule. And then the last one we want to deal with here is, let's name this 1, 2, 3, 4, 5, 6. So that's hex. There's all single bonds between the carbons, and there's no functional groups, so this is going to be hexane. Let's look for distribution of charge. That carbon and hydrogen, it's going to be within that nonpolar range, so when you subtract the electronegativity of carbon from hydrogen, it ends up being 0.4. That's still going to be nonpolar, and it's symmetric, so if you cut it in half, there's going to be lines of symmetry in either direction from there and there. So hexane is a nonpolar molecule. Alright, so you want to make sure for the molecules, check the geometry and the distribution of charge. Now let's take a look at CO2. We reminded you here that there are double bonds between the carbons and the oxygens. Let's go ahead and draw the lone pairs, there, and here and here. I want to see if the bond is polar or nonpolar, and if the molecule is polar or nonpolar. So we'll do the bond first. Okay, so recall, if we want to figure out what the bond is, we have to look at the electronegativity difference. So, carbon, if we look on table S, is 2.6. Oxygen is 3.4. And we'll do this oxygen is 3.4 as well. Okay. So, subtract them. 3.4 minus 2.6. And you just need to do these two. That's fine. And then you can do that too, those two, but they're going to be the same anyway. So, subtract them. When we do that, we'll find that this is 0.8. This is also 0.8. If we think back to our scale, from 0 to 4, this is 1.7, 0.5. The 0.8 tends to fall right here, which is in the polar range. So the bond is a polar bond. All right. Now let's look at the molecule. If we want to figure out if the molecule is polar or nonpolar, we have to look at the distribution of charge. Now we do know that there are going to be more electrons towards this oxygen. That makes this carbon partially positive. But hey, look, over on this side, the same thing happens. So when I cut this carbon, or cut the CO2 in half, and try to fold it on itself, it actually ends up having symmetry. Since you have an oxygen here and an oxygen there, when you fold it up, there is symmetry, and that carbon is being pulled by both oxygens. If you remember from the penguins and polar bear cartoon strip, this one should have been, the carbon should have been the penguins, the polar bears were the oxygens, and that penguin was kind of getting stretched from either end. So in this case, the molecule is nonpolar. So here we have a special example. CO2 is a great example of this. Don't forget it. You'll probably see this eventually. The bond is polar, but the overall molecule is nonpolar. Alright, so a quick little summary. If we want to know if the bond is polar or nonpolar, look at the electronegativity difference on table S, and make sure it's the absolute value. We don't need any negative values in there. Use that scale to help you. I'll sketch it one more time. And you should be able to sketch these on your own and just kind of remember these on your own. Here is your polar end. Here's nonpolar. And over here would be ionic. So you might be asked, which is more ionic in character? It's anything closer to that 1.7 or closer to 4. Whatever that difference is, it's bigger. So here you're just subtracting. If you want to know if the molecule... Oh look, my battery's low. Hold on. Almost done. If you want to look at the molecules to see if they're going to be polar or nonpolar, look at the distribution of charge. So look for any lone pairs and symmetry. If it's polar, it has unequal distribution of charge and is asymmetric. If it's nonpolar, it has equal distribution of charge and is symmetric. So, good timing here, guys. If you have any questions, please come see me. This is a super important concept, though, to know, and this is what tends to make a lot of Regents kids struggle. There's no reason for a struggle. Just make sure you go back through the notes again and let me know if you need any help. Take care. Bye.